Hey you guys, this is Jerry Pinter. Welcome to Chapter 3, Fourier Series Representation of Periodic Signals. In part 1 of this video, we'll be covering the continuous time Fourier series and frequency response. All of this is due to Mr. Joseph Fourier, the great French mathematician and physicist. So this chapter is broken up into 3 parts. In this first part of the video, we'll be doing the continuous time Fourier series and frequency response. And in part 2, we'll be doing the same thing, but for discrete time systems. Part 3, we will be dealing with filter theory. This will be our first introduction to filter theory, which we will return to later in the course as well. So let's start by looking at the representation of periodic signals using Fourier series. So you probably remember from math class, calculus class, for example, where you did a Taylor series expansion of a function. So the idea there was to take some function, let's say it's f of x, a function of x, and represent it as an expansion of a bunch of terms here. This is sort of like a power series because you can see different powers of x here. You could also do the same, arguably, with a function of time. So like if you had a signal x of t, you could do a Taylor series expansion of this signal and come up with these powers of time here. This, is all good and well, but there's a much better way of expanding a function for use in our signals and systems class, and that's what we're going to do next. So Fourier found out and discovered this brilliant idea that you could take a periodic function and expand it, or likewise decompose it, into a sum of a bunch of sinusoids. In other words, sines and cosines. And the frequencies of those sines and cosines are all harmonic frequencies, meaning multiples of the fundamental frequency. So basically a signal x of t could be represented by, you can see all these terms here, these are all cosines, and here there are a bunch of sines, and this is an infinite series, it keeps on going. Out in front of each term there are coefficients, and we'll be talking about those in more detail soon. The cosines, you can here use the letter b, so we have b naught just by itself, and then there's b1, b2, b3, and so forth, and the sines, we use the letter a for those coefficients. One of the key things here, though, is look at the frequencies of these components. The cosines and the sines are all multiples of omega naught. Omega naught is the fundamental frequency of the signal that we're dealing with. So remember from chapter 1, fundamental frequency is 2 pi over t, where t is the fundamental period. So we're dealing here in this chapter with periodic functions. Remember, these are functions that repeat themselves over and over. So you can notice here, like our cosine, the first term here is omega naught. The second one has 2 omega naught. And the third term, 3 omega naught, and this just keeps going. These are the harmonic frequencies, all right? So k times omega naught is the kth harmonic frequency. So we can write this in a little bit more compact notation by using a sigma notation here, the sum sign. And this is the Fourier series expansion of a periodic signal. So our signal x of t can be written as an infinite sum of sines and cosines, where you can see the frequencies are k times omega naught, starting with k equals 0 and going to infinity. Let's take a look at an example. This one comes out of your textbook. If you look in your textbook, figure 3.4 is where this is found. And what this shows is that this signal here, this is our x of t that we're going to start with. Notice it's periodic, right? It has kind of a, an odd shape, but it definitely repeats itself over and over. So this particular example here can be broken up into 4 pieces shown here. 1, 2, 3, and 4. And each of these pieces are a cosine function. Now the first one is when k is 0, all right? So that means the frequency is 0, and that means it's just a constant function. So this first term here, x naught here, we'll call it, is just turns out to be equal to 1 in this example. And that gives us actually the average value of one period of x of t here, all right? So this one, not that interesting, but the next three are all cosine functions. So this first one here, when k is equal to 1, this is called, the fundamental frequency or first harmonic. So omega naught, fundamental frequency in this example, is equal to 2 pi. And the coefficient out in front is equal to 1/2. So this first component here, or I should say second, this is really the first component. This component right here has a weight of 1/2, that's the coefficient, and the frequency is 2 pi, and it looks something like this. Now the next one is the second harmonic. That's when k is equal to 2. So it has twice the frequency, 2 omega naught, which in our example is going to be 4 pi. And the weight or coefficient of this term is equal to 1. That's why there's nothing out in front of the cosine. So it looks like this. So notice it's twice as tall as this one, because this one only had a coefficient of 1/2. And also notice it's wiggling twice as much as this one because its frequency is twice as high. And then the last component of this example is the third harmonic when k is equal to 3. So in this case, remember omega naught was 2 pi. So here we have 3 times 2 pi, which is 6 pi. That's our frequency. And this particular coefficient here is 2/3, which is shown right here. So the idea here is this original signal can be made by adding these 4 cosine functions together. All right, so we can say that the signal x of t has been decomposed into a cosine series consisting of just 4 components. Each component has its own frequency, k omega naught, and its own amplitude, b sub k. So this is b naught, b1, b2, and b3, and the frequencies likewise are 0, 2 pi, 4 pi, and 6 pi. So with just to continue this example, this leads us to something very important. This is the so-called spectral analysis of a periodic function. So we started with this function x of t. In other words, we're looking at what this signal is versus time. So this is the time domain representation of a signal. And this is kind of what we're normally used to. What we're going to do quite often in this course, in fact, you could argue that we're going to spend the majority of the rest of the course not in the time domain, but in the frequency domain. We are going to look at signals, how they appear in terms of frequency, not in terms of time. So for this example right here, remember that there were 4 frequency components at 0, 2 pi, 4 pi, and 6 pi. And the coefficients for each of those components were 1, 1/2, 1, and 2/3. Those numbers were shown on the previous slide. So this, this representation here of the signal is called the spectrum of the signal. It tells us what the frequency makeup of this signal is. So these are 2 different ways of representing a signal. And it's not that one is right and the other is wrong. They're both correct. They're just very different ways of looking at a signal. And oftentimes, this is going to be a much more powerful way to look at a signal in terms of its frequency makeup instead of its time makeup. And so, as I mentioned, we're going to spend a lot of the course working in this so-called frequency domain. So make sure you have these basic concepts understood in this chapter before we go on to more challenging and advanced topics in the later chapters. So, again, our idea here is that the signal x of t is completely described by its Fourier coefficients, and we can plot them as follows. So in this chapter, we're going to basically plot these coefficients in terms of k. So remember, for the first component here, b sub k was 1, and then it was 1/2, and then it was 1, and then it was 2/3. But remember, these k values just correspond to the multiple of the fundamental frequency. So, when k is equal to 1, we have 2 pi. When k is equal to 2, that corresponds to 4 pi. And when k is 3, that corresponds to a frequency of 6 pi radians per second. Now, what we just showed is all good and practical. However, it's more convenient and conventional to work in the complex Fourier series representation or expansion. And so the idea here is, instead of using cosines and sines, we're going to use Euler's formula and convert those cosines and sines into complex exponentials. So remember Euler's formula, e to the j theta is equal to cosine theta plus j sine theta. This can be sort of inverted to solve for sine theta, which is 1 over 2j times e to the j theta minus e to the minus j theta. And likewise, there is an expression here for cosine of theta. So we can basically take these forms here and plug them into the previous slide, into the Fourier series representation. And after doing a little work, I'm not showing the details here, it's shown in the textbook if you're curious, we come up with this form down here, which is mathematically more simple. Now you might be wondering, why do we do this? Why can't we just leave sines and cosines? The main reason or rationale for this is that exponential functions are easier to work with mathematically than sine and cosine functions. In other words, it's easier, much easier, to multiply exponential functions than it is to multiply sines and cosines, where you have to use a bunch of trig identities and can get real tedious and messy. So this expression here is a little more abstract because it's a complex exponential function, but it's much more compact mathematically and much more easy to work with. So we are going to work with this form here. So this is the complex Fourier series expansion of a periodic signal. A signal x of t is written as the infinite sum of a sub k, this is the coefficient, times e raised to the jk omega naught t. Now remember, omega naught is the fundamental frequency of x of t, which is 2 pi over its period. And notice up here in the complex exponent, we have k omega naught. That is the harmonic frequency. K is an integer times omega naught. And of course, that j there makes this a complex exponential function. Now, this equation right here is called the synthesis equation, because basically what it says is that any signal x of t that's periodic can be synthesized or made from a sum of complex exponential functions. Okay, if we write this out, it's going to look like this down here. All right, and this is, this is an infinite sum. Remember, it starts at negative infinity and it goes to positive infinity. So, you've worked with infinite sums like this in your math classes. The other equation here that's just as important is called the analysis equation, and it is the way you can determine what are these coefficients a sub k. So a sub k, the coefficients, are given by 1 over the period times the integral over 1 period of the signal x of t multiplied by e to the minus jk omega naught t, and this is integrated over time. And again, t is the period of our signal. So a lot of the problems involve, you're given some signal x of t and you want to find out what is the complex Fourier series expansion of this signal. Well, we have to calculate the coefficients a sub k by using this integral. And we'll do a few examples coming up shortly. One thing that comes to mind here is that our signal, signals are always real. Okay, we live in the real world. They're not imaginary or complex. So, but you notice that if we have a real signal here, how can a real signal be made of complex exponentials? because this has got a j in it. Well, if you expand this thing out like I did down here, all right, here's the k equals 0 term, and then k equal 1, k equal 2, and 3, 4, 5 going out to the right. If you go back to the left, it's k equal minus 1, minus 2, and so on and so forth. All right, so notice how these things pair up. A naught is a real coefficient, all right, so we don't have to worry about that. That one's well behaved. But notice these guys here are complex because they have the j's in them. However, it turns out, and you can actually prove it pretty easily, that a sub minus k is equal to the complex conjugate, see the little star there, of a sub k. All right, now how can I prove that? Well, very easily. If I replace this k here with minus k, the only other time I see a k is right up here. So if I put a minus k up there, that minus cancels this minus, and we have no minus sign up here. So what that shows is that a sub negative k is equal to the complex conjugate of a sub k. So notice this term here is the complex conjugate of this next term here. So we can pair k equal minus 1 with k equal plus 1, and we can pair k equal negative 2 with k equal positive 2, and we always end up with complex conjugate pairs. Now, one of the nice things about complex conjugate pairs is if you add them together, for example, if you add any complex number z to its complex conjugate, z star, you get 2 times the real part of z. In other words, it's no longer complex or imaginary. It becomes a real number. So this series here, even though it's composed of a whole bunch of complex terms, it's actually a real series. So let's go through some examples now of how we can calculate the Fourier series expansion for some periodic signals. So one of the first ones, well, the first one we're going to do is a classic example of doing a periodic Fourier series representation, and this is the periodic square wave. So again, you can look in your book. This comes out of the textbook. Figure 3.6 shows our periodic square wave. So you can see that this thing, is a rectangular or square pulse that appears every period. Here's t, here's 2t, 3t, and so forth. And we're going to let the width of this pulse be w. So this thing, notice we're going to center it right on the time equals 0 here. So it starts at minus w over 2 in time, and it goes to positive w over 2, and it has a height of 1. So our goal here is to find the Fourier coefficients of this periodic square wave. So here is our analysis equation, or the integral that defines the coefficients. This is taken from the last slide. So a sub k is 1 over the period times the integral over 1 period of x of t times e to the minus jk omega naught t. So let's go ahead and do this. Now remember, what this integral says here is we only have to integrate over 1 period. So we don't integrate over this whole thing. We just pick 1 period. So I'm going to start right here at minus minus w over 2 and go to w over 2, positive w over 2, because the value of our square wave is equal to 1 over that interval. So you can see I'm going to put my limits of integration from minus w over 2 to w over 2, and x of t is just equal to 1. So this is a very easy integral to solve. This is just an exponential function. So you know how to do this from your math class. Whatever is up here in the exponent in front of the t comes out in front on the bottom. So we have minus jk omega naught goes down here along, next to this period, t here. And then when we integrate it, we get the same exponential function, e to the minus jk omega naught t, and we evaluate it from w over 2, which is this term here, minus negative w over 2, which is this term here. And so this is the result of our doing our integral. Now, this is, a little bit of a mess. We've got, you know, we've got a j here, and we've got j's up here. So we can actually simplify this thing considerably by using a couple tricks here. So remember the sine, from Euler's formula, sine theta is 1 over 2j times e to the j theta minus e to the minus j theta. So if you look up here, you can see that theta is just jk omega naught w over 2. All right, and so we can see that fits in here, and so by making this substitution, we can rewrite a sub k as this shown right here. All right, now there's one other thing we can do here. Notice there's a couple of omega naughts. Remember, omega naught is 2 pi over the period t. So I'm going to go ahead and make that substitution in here because our original square wave is expressed in terms of w, the width, and t, the period. So making that substitution, I end up with this form here, and what we can do with this is a simplification. There's a function in math called the sinc function, which you may or may not have heard of. The sinc of theta is defined as sine theta over theta. So in other words, it's a sine function that's divided by its own argument. And this is what the sinc function looks like. You can see it oscillating, just like a sine function. However, the difference is it decays with theta because of this theta term on the bottom here. So by comparing this with this, we can see that this expression here is just w over t times the sinc function of k pi w over t. So here is our final result. This is the expression for the Fourier coefficients a sub k. So let's plot these out and see what it looks like. So again, what we're doing here is in the time domain, we have a periodic square wave, which is given by this. This is that same diagram from the previous slide. And our Fourier coefficients, a sub k, are given by this sinc function here. So when we plot them, it depends on the ratio of w to, this is the width, to the period t. So if we let the period be 2 times w, 2 times the width, we get this for the Fourier coefficients. Now you can kind of see the sinc function. See how it starts up high, it dips negative, and then goes positive, negative, and it sort of dies out as k gets bigger. That's because of this sinc function here. Look what happens if we let the period t equal 4 times the width. So what that means is we're spreading out these pulses farther and farther. And now we see a smoother kind of form of that sinc function. In fact, if we keep going, if we'll let the period equal 8 times the width, we get this result here. But this is the frequency domain, or the spectrum, and obviously it depends on, on the ratio of the width and the period here, but this is the spectrum or frequency domain version of the periodic square wave here. So each of these lines here, these represents the Fourier coefficient at that particular value of k. Let's just pause for a little bit here and talk about the convergence of the Fourier series. So in the previous example that we just did with the square wave, technically there are an infinite number of frequency components that are needed to exactly reproduce the square wave. So a couple questions come up. The first one, do we really need an infinite number of terms to make a square wave? And the second question, how can a bunch of curvy sine functions produce a square wave, right? Well, we can answer both of those questions just by doing a little bit of work here. So this is coming from your book in figure 3.9. But what's shown here is a single period of our square wave. So that's, the square signal right here. And if we only included one term in our Fourier series, then it would just be a single sine or cosine term. And obviously this, doesn't look very much like a square wave at all, okay? If we look at 3 terms, Well, it's still, certainly not a square wave, but one thing that happens here is you can see instead of just one hump up here, we've got two humps, right? So it kind of widens it out a little bit. Now look what happens when we go to n equals 7. Now this thing is starting to approach the general shape of our square wave. And so going to n equal 19 terms. So now we've got 19 sines or cosines or complex exponential functions all added together. And notice this thing is starting to converge and look more and more like the square wave. And when we get here to 79, all right, notice it fits really close. There you can still see, there's a few artifacts here. There's some overshoot and ringing, this is called. Notice how instead of just coming up to the corner here and stopping and going to the right, it actually overshoots a little bit, and then it kind of rings back in until it's right on the square wave, and then it rings here, and it does that down in these corners too. By adding more and more terms, we can actually reduce and get rid of those overshoots and ringings. But the idea here is very clear that as we add more and more terms, we start to approach our original function or signal much more closely. So we're converging to the actual function. And by the way, this is how a signal generator can construct a square wave or a triangle wave. It can basically add a bunch of sines or cosine functions together with the right coefficients and get to the point where it exactly mimics the signal that we're looking for. All right, let's do another example now. This one is going to be a lot simpler because we're going to use a trick. So in this one, our signal that we're going to try to expand is just a cosine function. It's a cosine of omega naught t. So, there's two ways to do this. The hard way would be to do the formal integral here. Remember our Fourier coefficients, a sub k, are given by this integral here. And so we could plug in, here's x of t, we could plug in cosine of omega naught t like I did here. And then at this point, we'd have to use Euler's formula and try to expand, either this term or this term in terms of cosines and sines or in terms of complex exponentials, and then, work with all those terms. It's doable. You can do it, but it's a considerable amount of work. A much easier way to do this is to do a trick basically by inspection. So remember Euler's form of the cosine. Our signal that we're trying to expand up here is cosine of omega naught t. So cosine of omega naught t is 1/2 e to the j omega naught t plus e to the minus j omega naught t. This is the Euler's form of the cosine. So let's distribute this 1/2 inside the parentheses. So we get 1/2 e to the minus j omega naught t plus 1/2 e to the j omega naught t. Now let's compare this result with the synthesis equation for x of t. Remember, the synthesis equation says that any signal, x of t, can be written, any periodic signal I should say, can be written as the infinite sum of a sub k times e to the j k omega naught t. So, we've got an infinite number of terms here, but the only ones I'm going to write down are the ones where k is equal to -1, 0, and +1. So here are those three terms. So look at the term for k equals -1. We get a of -1 times e to the minus j omega naught t. Well, this is the exact same term that's shown up here. Therefore, a of a sub -1 must be equal to 1/2. Now, a naught, there's nothing up here that looks like a constant. All right, so a naught is equal to 0. The last term, and the only other one we have to look at, is when k is equal to 1, we have a sub 1 times e to the j omega naught t. And again, if we compare that with this up here, we can see immediately that a sub 1 must be equal to 1/2. So we have just, so I can rewrite this here. Our cosine function, or x of t, is equal to 1/2 e to the minus j omega naught t plus 1/2 e to the j omega naught t. All right, and of course, this is just Euler's formula. But what this tells us is that for this function here, our Fourier coefficients are both equal to 1/2. When k is equal to 1 and when k is equal to -1, we have a 1/2. So here is our spectrum of a cosine function. We have a 1, when k is -1, we have a value of 1/2 right here. And when k is equal to 1, we have a value of 1/2 here. These are the only two coefficients a sub k. So this is our frequency domain version of a cosine function, or equivalently, we can say this is our spectrum of a cosine function. There are two components here at -1 and +1, and they're both equal to 1/2. Let's do another example. This one is very similar. This one is our signal x of t is equal to the sine of omega naught t. So we're going to use the same method. We're going to write the sine function using Euler's formula. So it's shown here. Now the only difference, the main difference, is that there is a j underneath here in the denominator, and there's this minus sign here. So again, I can distribute the 1/2j inside here, and I can compare and notice that when k is equal to 1, my a sub 1 must be 1/2j. That's the coefficient out in front. This is, this is our first harmonic when k is +1. And the other term here, it corresponds to the case where k is -1, because we see the minus sign up there. And so this term in front here, which is -1/2j, must be a sub -1. So here are our two coefficients, our two Fourier coefficients, and sometimes we don't like to put the j down in the denominator. Remember, your math teacher told you that was a no-no. So you can multiply the top and bottom by j, actually multiply top and bottom by -j, by the complex conjugate, to move the j up to the top. So this term becomes -1/2j, and likewise a sub -1 ends up being 1/2j. Now the big difference here, of course, is that this time the Fourier coefficients they're not real numbers, they're complex. Okay, they both have j's in them. So in this case, it's conventional to plot both the magnitude and the phase of these coefficients. So obviously, by looking at these two, the magnitude of both of these is just equal to 1/2. All right, so that would be our magnitude plot, is shown right here. This is, notice the absolute value bars around a sub k. So this is the magnitude of the Fourier coefficients, and then the this angle sign here means the phase of a1 is -pi/2. All right, because remember, a minus sign here means we went -pi/2, and so these are the phases shown here. By the way, these polar forms are shown up here. So we have a -j, all right, in this first one. Remember, this is from chapter 1. We learned on the unit circle, okay, -j, which is down here, has an angle of -pi/2 radians, or -90 degrees. So that's this guy here. And for this one, it's +j, right? There's no minus sign. And so +j has a phase angle of pi/2. That's this one up here, or +90 degrees. And so that's why this one has a phase angle of pi/2. So this one is a little more tricky, because we're not only plotting the magnitude, but we have to take into account the phase of these complex numbers here. Let's do one more example here where we're going to find the Fourier coefficients of a periodic function. So this time our periodic function, x of t, is an impulse train. So that means we have a series of impulses coming every period t. So here's one at t, at 2t, 3t, and so on and so forth. So again, our goal is to find the Fourier series coefficients, a sub k. So we're going to use this same integral here that we've used in the past examples. And what we have to do is substitute in x of t, remember, is a delta function. So that's the delta function shown right here. And we only have to integrate over one period. So we're going to go from minus t over 2 to positive t over 2. In other words, we're integrating from right here to right here. That's what we're going to consider as our period. And let's see, what we can do here is, this looks again at first sight kind of nasty, but it's actually not, because remember, whenever we have a delta function inside an integral, this delta function forces t to take on the value of 0. So what we can do is look for the t here, this e to the minus jk omega naught t. That t right here is forced to be equal to 0 by this delta function. Remember, this is the sampling property. We learned about this back in chapter 2. So this becomes e to the 0 here, which is just 1, and we can bring that out in front of the integral, and all we're left with inside the integral symbol is a delta function. And that's great news, because remember, the integral of a delta function is just 1, because the area under the curve of a delta function is always equal to 1. So this integral goes away, as does the e to the 0 power, and we're just left with 1 over the period here. So for an impulse train like this, its spectrum, or frequency domain representation, is just a series here of values, and each value is equal to 1 over the period, whatever the period here was, and it's the same value for all values of k, because notice there's no k in this result. In other words, every a sub k is equal to 1 over t, which is shown in this result down here. So at this point, you may be starting to ask, why are we doing this? What's the motivation for working with Fourier series and doing Fourier analysis, which we're going to be doing almost the entire rest of this course? Why do all this frequency domain stuff? Why take a nice basic real signal, x of t, and convert it into a messy sum of wiggling complex exponential functions? Shouldn't our goal be to make things simpler, not more complex? Well, the answer to these questions will become more apparent as we go on through this course, but in a nutshell, Fourier analysis provides a powerful tool for signals and systems analysis. And the reason for this is that for signals, all signals can be constructed from the same basic sinusoidal components. Thus, we have a common framework for building any signal. And then later on, when we work with systems, complicated convolutions, remember how fun those were in the last chapter. Convolutions in the time domain are going to be replaced by simple multiplication in the frequency domain. And this is one of the main advantages and powers of working with Fourier analysis, is not having to do these convolutions anymore. So as Mr. Fourier would have said, voila. Before we continue on with the lecture, I should also just mention that Fourier methods are used in a lot of different branches of physics and engineering. So obviously we're using them in this course. I'm also going to show you later on how to solve differential equations using Fourier methods, and it's really a powerful technique, and we can solve some of these differential equations by simple inspection once we know the methods. Fourier methods are used in acoustics, optics, oceanography, seismology, and also in branches of mathematics such as probability, statistics, and number theory. And it's kind of interesting that the most fundamental theory in all of physics, and you could argue in all of science, is called quantum field theory, which describes elementary particles and their interactions. And kind of the idea behind quantum field theory is, you learned in your physics class that when dealing in the quantum realm of the microscopic, particles are represented by wave functions. So what quantum field theory does is it takes that wave function and it basically calls it a field of the particle. So in other words, a photon or an electron would have some particle field like this. And we can, remember, we can decompose this field into a bunch of sinusoids by Fourier decomposition. And each of these sinusoids can be represented as simple harmonic motion, or you can think of a simple harmonic oscillator, kind of like the mass on the spring. And remember from quantum physics, a simple harmonic oscillator has quantized or discrete energy levels depending on the frequency of oscillation here. And so this is the the basic framework behind quantum field theory. It involves and uses at its very root, it uses Fourier methods. Okay, so let's move on and keep going here with our discussion of Fourier series representation. The next thing we're going to do here is just look at a few of the properties of Fourier series, and we'll see some of these repeated in the next chapters when we start talking about Fourier transforms. So I'm not going to go through all the properties. Your book has a list or a table that shows many more, but I will go through a couple of the ones that are probably the most important to us. The first thing we're going to do here is adopt some shorthand notation, which makes it a little easier to write things. So remember that if a signal x of t is represented as a Fourier series, we say that x of t is the infinite sum over all k of a sub k times e to the j k omega naught t. The shorthand way of saying this is that x of t leads to the coefficients a sub k, or you can think of it as x of t is associated with a sub k. So on the left here, this is the time domain representation of the signal, which is x of t. It's a function of time. On the right side is the frequency domain representation of the signal, and here we just are talking about these Fourier coefficients, where each coefficient is of course associated with a different harmonic frequency. So this is time domain on the left and frequency domain on the right. So our first property that we're going to discuss here is just the linearity property. So if x of 1 is associated with a sub k, and if another signal x of 2 is associated with the Fourier coefficients b sub k, then if we add, let's first scale x of 1 times some coefficient c1, and add that to x of 2 multiplied by some coefficient c2, then by linearity, the output of, this is some signal here on the left. All right, we've multiplied, and added these terms together. Well, the output basically by linearity has the same coefficients, but they're scaled by these same multipliers over here. In other words, we see C1 here and C1 here, and this C2 here multiplies by the B coefficients over here, and we're also adding it. So this is a linearity property. Another useful property that comes up is called time shifting. So again, if we start with our synthesis equation for x of t, which is written right here, what happens if we delay our signal x of t by some amount t naught? So x of t minus t naught, well, if we change this t here to t minus t naught, then we're going to have to change this t up here to t minus t naught. All right, so that's easy enough. What we can do next is use basically use our properties of exponents. All right, so I'm going to distribute the jk omega naught inside the parentheses here, and I've shown a couple of the exponent properties up here that we're using. When we have exponents that are added like this, we can break this up into two terms that are multiplied together, and that's exactly what I've done here. I put in parentheses the e to the minus jk omega naught t naught times a sub k, And then out here is e to the jk omega naught t. Now this last term here is the same as this term here. So what that tells us is that when we compare this in the blue box with our original expression here, our new coefficients, b, let's call them b sub k, must be everything inside the parentheses here. So notice that our new coefficients are the same as the old coefficients, a sub k, but they're multiplied by this complex exponential here, which represents a phase term, because this has a magnitude of 1. So here's our shorthand notation of showing the time-shifting property. If x sub t leads to a sub k, then x of t minus t naught leads to e to the minus jk omega naught t naught times a sub k. So in other words, time shifting changes the phase of the Fourier coefficients a sub k, but leaves their magnitudes unchanged. So if the frequency components are just shifted in phase to account for the time shift. And we can sort of imagine this graphically. If we start with this red sine function here, all right, this is our original function, so sine of omega t, and let's say we delay it a little bit by t naught, all right, well what happens then is we're going to shift it over, this is the blue curve here, it's the same sine function, but it's just been shifted or delayed in time, so this is sine of omega of t minus t naught. So what happens here is these two have the same magnitude, but what's differing here is their phase. And you can see that by actually distributing in the frequency and so forth. You can see this last term here represents the phase shift, which results from this time shift here. So that's kind of what the time shifting property tells us, is that a shift in time leads to a shift in phase of the frequency components. In the interest of time, I'm going to skip over the multiplication property. We'll return to this later in the course anyway, especially in chapter 4 when we talk about Fourier transforms. So let's move on. Also, I will sort of defer right now to the dual property of time and frequency domains. We'll explore this a little bit more in the following chapters. Okay, the second, in this first part of the lecture, there are two main topics that are equally important. The first one was this whole idea of doing a Fourier series expansion. And so that's what we've done up till now. The second part of this, at least this part of the lecture, the second half or whatever, is something called the frequency response. And here we're going to deal with the frequency response of continuous time systems. And this is another extremely important concept that we'll want to make sure that you understand in this chapter, because we're going to use this concept of frequency response over and over for the remainder of the course. So what we're going to deal with here is how a system responds to a frequency. And in particular, we're going to see how a system responds to a complex exponential that contains this frequency. So just a little bit of review here, and this is good to review some of the important things from the previous chapters. So remember in chapter 2, one of the main things we learned was that if you put an impulse into a system, right? This is the delta function, this spike here. It's sort of like kicking the system. How does the system respond to that kick or that impulse? Well, it spits out an output which we call h of t, which is the impulse response. Now, the other thing we learned in chapter 2 is that for any input to the system, x of t, the output, y of t, is equal to the convolution of x of t and h of t, where again, h of t is this impulse response up here. And one of the things we learned back in chapter 2 is that the convolution property is commutative. In other words, x convolution h is the same as h convolution x, and this is the formal convolution integral of h and x. Okay, so I'm going to write this here. So here's what we're going to do now in this chapter. We're going to let this input function up here, x of t, be a simple complex exponential like this. So e to the j omega t. And what I mean by simple is that there's just a single frequency here, omega, and this frequency is represented by this complex exponential function, e to the j omega t. So from this step here, we know that the output is equal to the convolution integral of the impulse response, h of tau, and e to the j omega t minus tau. So I'm just substituting e to the j omega t into this x of t minus tau here. All right, now what I can do here, again, is kind of simplify this a little bit. Notice I can distribute the j omega inside the parentheses here. So I have j omega t minus j omega tau up there in the exponent. So t, notice, is not the variable of integration. We're integrating over tau. So I can pull out the e to the j omega t out in front. And what I leave behind is this integral of tau. However, when I integrate this, I'm integrating it from minus infinity to positive infinity. So this is what we call in math class a definite integral, not an indefinite integral, right? We're integrating from two values here. So what happens is the result will not be a function of time. It's going to be a function just of frequency. All right, and this will become more clear when we actually work through some examples. So our output of this system is equal to e to the j omega t, which, by the way, is exactly what we put in, multiplied by this function here, which is called the frequency response. This integral here is, we're going to call this big H. You notice uppercase H, not so we don't confuse it with lowercase h here. It's uppercase h, and it's a function of j omega. All right, omega being frequency, and the j we put in there just to kind of remind us that this is in general going to be a complex function. So here's our result again, and this gives us the idea of frequency response. If we put a frequency into our system in the form of this complex exponential here, e to the j omega t, the system spits out the same frequency. Here's e to the j omega t again. That's just our input. The only difference is the input has been modified by this function h of j omega. And when I say modify, what the frequency response, this h of j omega is called the frequency response. What it does is it changes the magnitude and the phase of the input, but not the frequency. Okay, so the frequency stays the same, but its magnitude and phase are going to depend on whatever this function big H of j omega is equal to. And once again, the frequency response, we got this from the last slide, we can calculate what the frequency response of the system is by taking the integral of the impulse response, h of tau, times e to the minus j omega tau, and integrate that over tau. All right, and so we'll be doing examples of this shortly, which will give you a little more experience with this. Just, you know, a final note here that the frequency response, h of j omega, is an extremely important function because it tells us how the system responds to specific input frequencies. And so we'll be dealing with frequency response throughout the rest of the course. All right, let's go ahead and do an example. So here's an example of calculating the frequency response of a system. So let's say we're given an LTI system has the following impulse response. All right, h of t, little h of t, is equal to e to the minus t times a step function u of t. So what this means is that if we put this impulse here, this delta function, into our system, it spits out the impulse response, h of t, which looks like a decaying exponential here, okay? So our goal is to find the frequency response, big H, of j omega of the system. So from the previous slides, the frequency response, h of j omega, is equal to the integral over all time of h of t times e to the minus j omega t times dt. So let's go ahead and calculate this integral. So h of t was given to us. It's just e to the minus t times a step function. So we can put, we can replace h of t with e to the minus t. The other important thing here is that these limits of integration go from minus infinity to infinity. Well, since we're using a step function here, we have to change the limit of integration from 0 to infinity. Okay, so you can see this integral now looks like the following. And also, we can combine these exponents. You know how to do that from all your years of math classes. And I'm going to combine them by adding the two exponents together and factor out the t. So I get the integral of e to the minus quantity 1 plus j omega times t dt from 0 to infinity. So this is a very simple integral. It's an exponential function. So remember, whatever is in front of the t goes underneath here, out in front, and there's the minus sign. And then when we integrate it, we have the same. The integral of an exponential function is just that same exponential function, and we have to integrate it from infinity to 0. So what happens here when we plug in the infinity up here? Notice that this is e to the minus something times infinity. So e to the minus infinity is just 0. So I have 0 minus, and then we have to plug in 0. So this is e to the, notice the t becomes 0. So this is e to the 0, which is 1. So I end up with 0 minus 1, which is negative 1. That negative 1 cancels this minus sign. So, obviously I didn't put all those steps in here just because this is a simple integral, but, you should be able to do that integral on your own. Make sure you can understand how to do this basic integral here. And once we're done with that, we end up with, since remember this is a 0 minus 1, all we're left with is this. This is our frequency response of this signal. H of j omega is equal to 1 over 1 plus j omega. So let's put this back into our system diagram here to see what this means. If we have a signal coming in, e to the j omega t, the system is going to spit out the same signal, e to the j omega t, multiplied by our frequency response, which is 1 over 1 plus j omega. Now, since h of j omega is a complex function, and it usually will be, we're going to plot its magnitude and phase. Well, the good news here is you already did this. If you go back to homework 1, one of the problems on homework number 1 was to plot the magnitude and phase of this function right here. So you've already done this. You used the Pythagorean theorem to find the magnitude, and you used the right triangle trigonometry to find the phase angle. So here were the results. H of j omega, the magnitude, looks something like this. All right, and this is the phase plot over here. So this is the frequency response. These two plots together comprise the frequency response of this system that was given to us. So let's try to put a little physical meaning into what is, this is all kind of abstract stuff, this idea of frequency response and so forth. So what is this really telling us about this system? Well, it's actually quite simple. If we look at this frequency response here, notice this is a plot of frequency down here, not time. So at low frequencies, all right, meaning frequencies near 0, the frequency response is just 1. Okay, and notice there's no phase change or anything, right? It's near 0. So this means that this system for low frequencies, all right, 1 over 1 plus j omega is just basically equal to 1. So at low frequencies, this input frequency goes right through the system and comes right out unchanged. Okay, in other words, low frequencies are passed by this system. What about high frequencies? Well, notice as omega gets big, well, look what happens to our frequency response. It gets lower and lower and lower, and it starts to approach 0. So this means for high frequencies, this system blocks the signals and doesn't let them out. So if we put in a high frequency over here into this system, what comes out is basically something very small or approaching 0. So in other words, this system is what we call a low pass system. It passes low frequencies and it blocks high frequencies. And this is our first glimpse at what a filter is. All right, this would be considered a low-pass filter because it's filtering out high frequencies and passing low frequencies. So we'll return to this concept in part 3 of this chapter's lecture later. There's another interpretation of the frequency response that may be useful to some of you, or it may not be. It may just confuse things even more. But if you've had a class, for example, in quantum mechanics, or taken advanced calculus class, we can sort of use this idea of an operator and eigenfunctions and eigenvalues, and it's very similar. And in fact, it actually is exactly that. The idea here is that our system, our LTI system, behaves as an operator that takes an input signal, which is the eigenfunction, and it returns the same eigenfunction multiplied by an eigenvalue. And so this is something, you know, again, that you saw in your quantum mechanics class, or in one of your advanced math classes. So the system basically is like, you know, kind of like a matrix in a way. It operates on this eigenfunction or eigenvector, if you want to call it that. And the key thing about eigenfunctions is that when you operate on an eigenfunction, you get the same eigenfunction back. You get it back, but it's been modified by an eigenvalue. So in this case, in this context, our frequency response basically takes or assumes the role of an eigenvalue, and our input function assumes the role of an eigenfunction, and the system is an operator. So this is, you know, we're not going to really use this these ideas any further, but this might help clarify some of these concepts when you can kind of compare it to something you're already familiar with. All right, let's go on and do something a little more practical here for the last example that we're going to do shortly. We can use properties of linearity and superposition to find the system output y of t for any periodic input to the system x of t. So we already learned, you know, in the last few slides that if e to the j omega t goes into our system, then we get the same e to the j omega t out multiplied by the frequency response h of j omega. So I'm going to do two things now. I'm going to multiply this input signal by the coefficient a sub k. So by linearity, I just multiply the output by a sub k. The other thing I'm going to do is I'm going to let this frequency omega be a multiple k of the fundamental frequency omega naught. So I'm just replacing omega here with k omega naught. So obviously I need to do the same thing over here. This omega and that omega are both replaced with k omega naught. The last thing is I'm going to take this input now over here, and I'm going to sum over all k. Right, so I'm going to put a sigma symbol there, and remember, you know, this is a linear system, so superposition works, right, by linearity. So therefore, if I sum all the inputs together, then my outputs also become summed. So what this means is that this summation on the left side, the reason I did all this is because this is just the synthesis equation for a signal which is called x of t. All right, and on the right side, our output of our system is this mess here. Well, this is another synthesis equation. The only difference is that the coefficients are the stuff underlined here in red. So what this tells us is the following. If we have an input signal, x of t, that has Fourier coefficients a sub k, and we know how to find these coefficients using any of the methods we've discussed previously in this video, then the output of the system is equal to this, the output of the system is a signal whose Fourier coefficients are the same a sub k, but they've been modified by the frequency response at the particular harmonic k omega naught. All right, so this just means that if we can find the frequency response of a system, and we know how to do that from the impulse response, and if we can find the Fourier coefficients of the input, we can figure out what the output Fourier coefficients are, and then working backwards, we can find the output of the system. So, notice we can do this there's no convolution involved here. So it's kind of abstract, and it sounds like kind of a mess, right? When you first see this. But the main idea here is that you can find the output of this system here without doing any convolution. And the reason for that is because we're working in the frequency domain instead of the time domain. So let's go on and do an example. All right, so actually before we do the example, let me sort of summarize. There are two ways we've now learned to determine the system output. So in chapter 2, we learned that in the time domain, the output is the convolution of the input and the impulse response. In other words, if x of t is going into our system, then our output, y of t, is equal to the convolution of x and h. All right, but we saw in chapter 2 that this is not an easy thing to compute. All right, convolutions can be very tedious and tricky to do, especially by hand. We've now learned a new method of figuring out the output. It's by working in the frequency domain. We're going to simply use multiplication of an input's Fourier coefficients and the frequency response. So in other words, if the input x of t has Fourier coefficients a sub k, then the output y of t has Fourier coefficients b sub k that are equal to the input Fourier coefficients a sub k multiplied by the frequency response at that particular harmonic frequency. All right, so now I think we're ready to go ahead and try an example using this method down here. Okay, so in this example, we're given an LTI system with the following impulse response. And actually, just to make our life a little bit easier here, I'm using the same system that we analyzed earlier in this lecture. So this system has the impulse response e to the minus t times the step function u of t. You remember this one here. The impulse response is a decaying exponential function. So our goal here is to find the output y of t when the input signal is a cosine function, cosine of omega t. So here is our input going into this, this same system here. We're going to put in, not an impulse, but we're going to put this cosine function into it. What does the system produce for an output? So one way to do this problem is you could do the convolution method. The output here would be the convolution of this function here with this signal here. And that would work, certainly. But what we're showing now is we have another strategy to do this. We're going to find the coefficients, the Fourier coefficients, b sub k, of this, we're going to find the Fourier coefficients of the output here by using the Fourier coefficients of the input. And we already did some of this work, all right? So the idea here again is the whole works of how we're going to do this. But basically, we're going to find the Fourier coefficients of the input, where the input is cosine of omega t, and we're going to then find the Fourier coefficients of the output and work backwards to find y of t. So let's go ahead and do this. Okay, so the first step is we've already found the Fourier coefficients for cosine omega t. We did it in an earlier example. Remember, it has only two coefficients. A1 was 1/2, and a of minus 1 is equal to 1/2. And also the frequency response of this system we found also in a previous example. So if the impulse response is e to the minus t u of t, then the frequency response h of j omega is 1 over 1 plus j omega. So if we replace this omega here and this omega with k times omega naught, here it is here, k omega naught, this is our frequency response for this particular system for any harmonic frequency k times omega naught. All right, so let's find the Fourier coefficients of the output y of t. So what we're going to do here is, all we have to do is plug in, remember, b sub k is equal to a sub k times this here, the frequency response. So I'm going to take this result over here on the right, and just put the a of k on top because we're multiplying this, all this, times a sub k. So when k is equal to 1, remember a sub k was equal to 1/2. So here's the 1 over 2. That's the 1/2. So there's our b1. And when k is minus 1, our a sub k was also 1/2. That's up right here. So here it is again, 1 and 2. Now the difference here, though, is k is minus 1. So remember, this k right there becomes minus 1. So that introduces that minus sign right there. But these two results here shown in the yellow boxes, these are the Fourier coefficients, the b sub k, for our output. All right, so the last thing we have to do now is to figure out what is our output y of t in the time domain given these Fourier coefficients in the frequency domain. So we're going to we can use the synthesis equation here. So y of t, our output, remember, is a infinite sum of b sub k times e to the j k omega naught t, but we don't have to do an infinite sum. There's only two terms in the sum, when k is 1 and when k is minus 1. So here are those two terms written like this, okay, taken right from this summation here. And of course, b of minus 1 is this in the yellow box, so that's shown here. And b of 1 is this in this yellow box, and that term is shown here. So here is our output. Now, we could leave it like this, but this is not too meaningful because this is not a real function. And we require, this is a real system, so it needs to produce a real output. But it turns out that we can convert this into a real function, which we will do next. Okay, so from the previous slide, or the previous step in our solution, we can notice that y of t here is the sum of these two terms. I just retyped them here. But notice that they're complex conjugates of each other. Wherever there's a j here, there's the opposite of j here. Likewise, this j here, we have opposite of j here. So the signs of all the j's flip. So that means that if we call this term z, then this term here is z star, or the complex conjugate of z. So we end up with our output, y of t, is z plus z star. Remember, I showed you this earlier, that a real useful property here of complex numbers is if you take a complex number z and add its complex conjugate to it, then you get 2 times the real part of z. So our answer is 2 times the real part of this in brackets here. This is z. So by using Euler's formula, we can write the top as a cosine and a sine. And to remove the j from the denominator, we multiply top and bottom by 1 plus j omega naught, which is the complex conjugate of this term here. And so when I do that, it looks like this. And now I have to do, a little bit of algebra. I have to distribute or FOIL, the numerator here. And likewise, I can distribute or FOIL out the bottom, okay? And I end up, I'm grouping all the real terms together here, all the imaginary terms, with the j over here, and then there's the denominator. And remember, we're trying to find the real part of this. So the nice thing is that we can ignore all the stuff in brackets here, because that is the imaginary part of this whole solution here. So the real part of this solution, and multiplied by 2 out here, is this down here. So notice this answer here, which is fairly complicated, but it's really got just 2 terms. There's a cosine term here, and there's a sine term here, and notice everything is real. There are no j's left in our answer, and we can see that there are coefficients out in front of the sine and cosine that depend on omega naught. By the way, that solution there, I mentioned, the other way to do this problem is by convolution. And this one actually is not that bad using convolution. I won't go through the details here because this has been kind of a long lecture. But if you perform the convolution integral, it looks like this up here. And then by using Euler's formula to get rid of this cosine and turn it into complex exponentials, you can write it as follows. And finally, by distributing these terms out and doing the integrals here, you end up with this form here, which is the exact same form that we found about halfway through our other solution. So from here on, the solution is precisely the same, and you'll get the same answer. Okay, so you guys, that is the end of this. Turned out to be a fairly long lecture, but we learned two out of the three really important things in this lecture. We learned about Fourier series expansion, and we learned about frequency response. In the next part of this video, we're basically going to do the same thing for discrete time signals. And you know, the good news is that all the concepts are pretty much the same. We just have to do, you know, make some appropriate changes to deal with discrete time systems. Until then, that's it for now, and I will see you shortly. Goodbye.